All right. So our test is Thursday. Our test is going to be entirely calculator, right? All with the calculator. Now it's important when it's a calculator, especially to have your notation set up because you have to indicate where your answer is coming from. If you just have an answer that appears out of nowhere, you're not going to get credit even if it's right. Okay. There's almost like a higher burden of proof because you're using the calculator. So if you keep this in mind, you should be good. You should never ever ever pick up a calculator to do anything on it unless you already have that you're going to be doing on the calculator written down on your paper. Okay? Written down on your paper or your iPad, whatever the case may be. Because your calculator is only there to do the heavy lifting, to do the number crunching. It is not a substitute for thinking. You're the thinking partner in that relationship, right? Who's the boss? You or the calculator? The calculator, right, is not the boss. Very good. You tell the calculator what to do, not the other way around, okay? So notation. If you just have an answer appearing out of nowhere, like I see a bunch of y'all do, which is nice that I let you try to do that, you'll get 0 points. 0 points. We call that a bald answer. That's what College Board calls it, a bald answer. Not to bring y'all down again, but speaking of bald, Mr. Engler was bald. Someone brought this to me this morning. They want me to give this to the family. They made it last night. It's Mr. Engler is the light, and it has the sun kind of rising on the horizon in the darkness of night. And I don't even know who this student is, but she gave it to me. And I said, you know what? That actually kind of looks like Mr. Engler, right? He was bald. The sun with no hair, it kind of looks like Mr. Engler, right? So they'll like that. Bald answer. So let me show you what you have to write to get credit. Okay. First of all, let's turn the calculator on. Everyone has access to this one that I'm using, right? At home or at play. But when you're in class, feel free to use the color one or your 83. Now, when you turn in a calculator of mine, make sure you reset the memory. Let's review that quickly. Second plus takes you to the meme generator, right? mem. It's memory, unfortunately. Second plus, right? And then you go to 7. You can just type 7. That's reset. Don't just hit enter. We don't want to reset the RAM. We want to reset all of it. So click to the left once or to the right. I don't know if y'all have more memory tabs than I do, but you want to go to all, right? Then you hit enter, and then you have to confirm it by hitting number 2 or reset, and then it should say memory cleared, right? So always do that before you turn in the calculator. All right, now we go to y equals. We're going to use y equals not just as a place to go to type something in so we can graph it, but we're going to use it as a repository of functions that we can recall from the home screen. Now, because we're going to be using y1 several times, it's super important that you type it in correctly, okay? Type it in correctly. So I'm going to come up with a kind of a checklist here. I added another page. Step 1, type it in correctly. So 2x, you got to use x on the y equals screen. Someone asked yesterday if they could use a different letter. And I was like, sure you can, right? But you can't. From the home screen, you could choose a different letter if you define it. But on the graphing screen in function mode, when it's y equals, you have to use x. So I learned something the other day. It's got to be x. So 2x caret 3, right? You have to use caret 3, and then you click to the right to get out of the exponent. And then minus 3x squared. So you could use the x squared key, or you can do caret 2 and click to the right. I'll use the squared there, which puts me back on the ground automatically. Minus 3x plus 2. Double check, triple check. Make sure it's in there correctly. Hit enter. Boom, I got it. So here's your kind of checklist, right? Number 1, put it into y equals and triple check. Triple check to make sure it's right. All right. Number 2, don't hit graph. Don't hit graph. You want to hit zoom 6. When I put these in little boxes like that, that means that those are the buttons that you press, okay? Zoom, and then 6, remember, is your standard viewing window. That's -10 to 10 on both the X and Y axis. That's a good place to start if you don't know what the graph looks like. All right. Now, what we're trying to do is we're trying to capture all the local behavior. The local behavior is what again, right? Well, it's not the end behavior. That's infinity, negative infinity. The local behavior is all the interesting stuff about the graph. That would be its x-intercepts, which we see all three of them here. It would be its y-intercept, which we see here. And it would also be like any discontinuities, vertical asymptotes, holes. We don't have any of those. But it's also like the local maximum. Remember, we call that a local maximum and the local minimum. And we see those here as well. Now, if we look off the graph, it could be that the graph dances around and turns off the screen above and below, but because it's a cubic polynomial, it actually, we know it doesn't, okay? So we have captured all of the local behavior in our standard Zoom 6 window, which is nice. Again, this worksheet was created for the academic level. On your test, it may not be. You may have to zoom out, you may have to zoom in, and we'll work something like that tomorrow, okay? Now, what you could do, if you wanted, is you could trim off some of the fat, right? The math butcher. We don't really need to see to the left and right of it looks like -4 and 4. And then the high and low point, the local max and min, again, look like they're within -5 to 5. So you have some options. I wouldn't necessarily do that here, but let's review it, okay? Number 3 is going to be change your window or zoom, okay, to capture the local behavior and do your math homework. Because we're going to test on Thursday and we're departing from 4.1, the worksheet for 4.1 and the notes for 4.1 are not due on Thursday. We'll finish that when we get back from Thanksgiving break, okay? We're just going to squeeze in a calculator test here. All right, so again, I wouldn't do that here, but here's a couple of ways to do that. You could either do that by manually changing the window. All right, click on window up at the top. There's really 2 settings that you want to change. Your X window, min max, and your Y window, min max. Right now we're at -10 to 10. I think if we change that to -5 to 5, it should be good. All right, so let's try that out. Remember, negative is down on the bottom right. Don't hit the minus sign. So -5, enter, to 5, enter. Your X scale, you can leave it at 1 or you could turn it off. Sometimes I put it at 0. We really don't even need to see it. But that's how often it puts a tick mark. Now your Y min, Y max, I think we could also go -5 to 5. The high point and low point were kind of small values. Your Y scale again, how often do you want a tick mark? I usually turn that to 0 when I zoom out because you don't want fat axis, but we'll leave it at 1 for now. Again, you can put it at 0. After that, your X resolution and your delta X or your trace step, that's just how often you want it to put a mark, or when you trace, how often you want it to jump from one point to another. You can leave that all default, okay? Now hit graph, and you're like, oh yeah, there it is. I zoomed in, essentially, right? I zoomed in. I still see the local behavior. What else could we do? Well, let me show you another option. If you hit zoom, memory, you could do previous. Now, our previous window is just the standard window, Zoom 6. But let's say that you had a customized window and then you changed it to see if it would be better. And then you're like, oh, crap, I don't like that window. It's kind of like an undo button. You know, these calculators are not like Notability. You can't just undo, but you can, right? If you hit zoom and you click to the right to memory, the very first one is Z previous. Hit enter and it takes you back to what it was before, which for us was just Zoom 6, okay? But it's nice to know that. Now, here's another thing you could do. If you want to capture the local behavior and you don't want to manually type it in, hit zoom, right? You can hit zoom, and I like number 1, zoom box. When I say zoom box, I always think of that Hanson song. Zoom box, 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 ooh, Dibby wop wop zoom box, 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 ooh, yeah. Whoa, whoa. Just me? Okay. Now let's hit enter, zoom box. You're going to have a blinking cursor at the origin. What you're going to want to do is define two diagonal corners of a rectangular box that contains your local behavior. So I always like to start in the top left corner. So I'm going to scroll up to above where the local max is, and then I'm going to scroll to the left of where the x-intercept is, up and to the left, okay, somewhere in there. And it varies for each person, but I think that's good. Now I'm going to hit enter, which locks in that corner. And now all I got to do is scroll down and to the right, and you could do them one at a time, or you could do a little at a time. You can scroll all the way to the right and then all the way down, or you could just go down right, down right, down right, down right, down right, down right. This is downright fun, isn't it? Down right, down right, down right. Yeehaw, downright fun, downright fun. There you go. I have captured now my local behavior in that little box. Okay. If you hit enter now, what's cool is your box could be like a tall, skinny rectangle or a short, squatty rectangle. It'll rescale your axes, to that box, which is cool. Mine is still relatively square. And there it is, right? Pretty cool. So zoom box is nice. Now I'm going to go back to where I was before, okay? Zoom previous or zoom 6, either one. There's another one that I don't use that often, but some people do use it. If you hit zoom, you can also do number 2, zoom in. It's zoom in, it's number 2, okay? #2. Now, what zoom in does is it gives you a single scale factor. If you imagine just like a pinch zoom on a calculator, right? When you put your fingers down and you open your fingers, it zooms in both axes, right? X and Y. Same thing here. See how it's blinking at the origin? You can move that to the center of where your pinch zoom would be, okay? So you want to put that kind of in the center of your information. So I just move mine to the right and up. So if I were to zoom in on this graph, that's where I would put my pinched fingers, and I would zoom in so that the scale would be there. All right. So you don't pinch zoom, you just put it there where your pinch would be, and you hit enter and you zoom in. So notice that's not the best one for me. I did capture the local max, but my local min is off. So now if I wanted to, I could go in and manually change my Y min to something lower. So these are all just like exploratory skills, right? We're exploring. Okay, now I'm going to go back to where I was before, zoom 6. And let's do one more here that I didn't do last period. Let's click zoom and let's zoom out. Here's why we might want to zoom out. Remember I said a little while ago that we're pretty sure we caught all the local behavior, but how do we know for sure that if this graph exits the bottom, it doesn't have some more local max and mins over here? Or if it exits the top, how do we know it doesn't turn around anymore off screen? Well, if we know the equation is a cubic, it turns out a cubic can have only 2 local extrema, just like a quadratic degree 2 can only have 1 vertex. By the way, we don't call these vertices anymore. We call them local max and mins because a vertex is only for a parabola because of the symmetry. So if we were to zoom out, it would be a real quick way to see if there is anything else. Now, let's zoom out. We did this, I think, with end behavior. Zoom out is number 3, okay? And again, this zooms out at the same scale. So let's just leave it at the origin. I'm going to hit enter. Do you see it turning around anywhere? No, I don't either. Now, you could zoom out again. Once you're in zoom out mode, like trace mode, you can keep hitting enter. So I'm going to hit enter again. Now, because I'm zooming out at the same scale, notice I'm not just seeing higher and higher, but I'm seeing wider and wider. So my skinny graph looks like it's becoming the y-axis, right? This is like us going into space. Let's hit enter one more time. We're Jeff Bezos, right? Do we see the graph on the ground anymore? No, let's go up one more time. Hit enter. Hey, look, we're astronauts. We're astronauts. Not really. We're astronauts. you have to do something when you're in space to be an astronaut now, right? So what are we going to do now that we're up there before we come down? Quick, we want to be an astronaut. Someone tell a joke, right? Does that count? If we tell a joke in space, we're astronauts. No. All right. Now, just as soon as we went up, zoom 6, we come back down. Okay. So zooming out is not bad if you want to just make sure that there's nothing else going on out there that you're missing, right? It's a real quick way to do that. But you do lose the local behavior, right? So there's all your zoom features. That's all the ones that we really need to know. Okay. So now that I know that I've got all the local behavior captured, let's go ahead and answer the question. On a calculator portion, you need to write the notation. You need to have it written down. It says find f of 2.5 and determine if it is increasing or decreasing. Now, truth be told, Mrs. Lincoln typed this up and she typed it up very quickly. I would have edited it a little bit, and this is one of the privileges I have of teaching the top level math here. As I go to training for College Board and stuff like that, the notational thing trickles down to the other teachers so that the same language can be used across all sections. But we don't want to use pronouns in here, like it. Okay, you have to have a real clearly defined antecedent, and a lot of the times that's not there. Okay, in this case, the antecedent would be f of 2.5. Well, f of 2.5 is just a y value. A single y value can't be increasing or decreasing because it's a single value. But what can be increasing or decreasing at that point? The entire function. Okay, so this is what I would say. Find f of 2.5 and determine if f or f of x is increasing or decreasing. And then I would say at that point or at x equals 2.5. Okay. When we talk about a point on a graph, we can either talk about it A as an ordered pair or B as an x value. I know an x value is not a point per se, like a coordinate, but think of the x-axis as time. Okay. Determine if the function is increasing or decreasing at 2.5 seconds. Determine if the ball is going up or down at 2.5 seconds, right? So that's when we say at that point. It's like a point in time. So you never just refer to the y value. You don't just say when y equals whatever. So this is how I would write it, okay? Now we're going to write in complete sentences, right? Because we are honors, and it's a little bit higher expectation. Now, what do we have to write to get credit? You have to rewrite f of 2.5. You have to rewrite that. You can't just piggyback off what the instructions are, because then if you come up with your answer, I don't know which part of the instructions you used. Did you use the part that said FIND? Did you use that somehow to find 7? Or what did you use? Well, when you say f of 2.5, you've got it. Now, there's a couple of ways to evaluate it, right? The first way is easy. From the calculator graphing screen, hit trace, right? You can hit trace, and then you just type in x equals 7. Oh, I'm sorry. I'm getting the answer. I'm looking at Jill's paper. I don't even write trace nice. Hang on, let's back up. Trace. And again, it doesn't appear to be ready to accept an input, but it is. I'm just going to put from the graphing screen. Right? You hit trace, and then you just type in 2.5. 2.5, enter, and boom, it tells you it's 7. Okay. So there's two ways to write your answer. You can either say f of 2.5 equals 7, side by side, right? Or you could say f of 2.5, and then below there you put 7 without an equal sign. That's it. One of those two ways. Okay. Now, the nice thing about having the graph with the local behavior contained, or at least the x value that we're looking at, is if you can see the y value there, it's a blinking cursor. And we read a graph like we read a book. Yes, from left to right, from cover to cover. It's good. From left to right. Is the graph going up or down at that blinking cursor? That's right. It's going up. It's going up, right? It's going up. Just like our spirit, just like our pride. It's going up, up, up. Let's raise the roof. Okay. So Don't just write increasing. Complete sentence, okay? So here we go. F, or f of x, is increasing at x equals 2.5. Boom. That is doing some math, people. That makes my heart swell with pride when I see y'all write that. Notation, notation, notation. No bald answers. Complete sentence, subject, verb, predicate, period. Nice, nice. F, or f of x. Okay. Now, is your value that you're looking at always going to be on your graph screen? No, not necessarily. So this is nice. This is cute. This will work when it works, but it won't always work. So we're taking it to the honors level now. I would encourage you to get in the routine of doing it on the home screen, because the graphing screen won't always work, especially when I'm writing the questions. So let's review the other way to do it, okay? Or from the home screen, right? You're going to hit alpha, trace, alpha, trace, and then we're going to select Y1, right? This is going to be from the home screen. And remember how to get to the home screen? You hit second mode, right? Do we need to write that up here? Second mode gives you to clear, right? To clear everything, to get back to the home screen. To get to home screen. All right, so from the home screen, alpha trace unlocks your F4. We have it in Y1. And then remember, we do open parentheses. And then we type in our 2.5. And then close parentheses. And we get 7. Okay, so that's the other way to do it. Now, what's the drawback to this? To see if it's increasing or decreasing, we don't have that visual anymore. So when you're flying an aeroplane, right, you don't always fly by sight, right? Some of the bush pilots in Alaska, that's all they do. They fly by sight. But any good pilot is going to also know how to fly by instrumentation, right? Because you won't always have line of sight, right? Or if you're a blind pilot, you have to fly by instrumentation, right? Yeah, I don't know. So let's go ahead and fly by instrumentation. Let's go ahead and use the data. How can we determine from the home screen here if at 2.5 the function f of x is passing through there going up or passing through there going down? Think of the x value as time. At 2.5 seconds, is the ball going up or down? If we knew, what if we knew the height of the ball? That is, what if we knew the y value in the very next instant of time? Like, what if I knew where the ball was at 2.6 seconds? Would I be able to compare it to where it was a tenth of a second ago? Yeah. Now, that's not a guarantee. If you let a tenth of a second go by, in theory, something can go up and down several times. But a tenth is actually kind of safe. So let's go ahead and do that. Let's see what the y value is in the very next instant moving forward. Now, you don't have to write it down. This is just for your own benefit. So alpha trace, enter, of 2.6. I would say as a rule of thumb, go a tenth. Don't go 1 unit. Don't go to 3.5. Just go a tenth, 2.6, and compare it. A tenth of a second later, if you will, it's taller, right? So we could say then what? The function is doing what at 2.5? Increasing, right? Now, you could go back in time, right? 2.4, but then you have to readjust your brain, right? Like, oh, that's what it was before. So it's easier for us to go forward than rewind. Yeah. So that's a good way to do it. Okay. Got it? All right. And then we write the same sentence. Okay. So let's go ahead and I'm going to change part B. I'm going to change part B because 0.5 is an easy number. I want you to find, let's write this. I want you to find f of negative 13 and determine if f of x is increasing or decreasing at x equals negative 13. Okay. So I want you to do that right now. I'm going to pause the recording and then I'll be back. All right. So I'm going to do it with you from the home screen. Well, let's do it from the graph screen, right? Mr. Corby said to do it from the home screen, but I'm going to secretly do it from the graph screen. That's fine. I don't really care how you do it, as long as you're accurate to 3 decimals and you never use a rounded number for a subsequent answer and you get the right answer and you're writing complete sentences, all that good stuff. So if this is the instructions, right, I'm just going to pretend like this was here. So I'm going to rewrite it now. This is me declaring the answer, f of negative 13. I'm going to go side by side here. If I hit trace negative 13, I'm going to get error invalid, and then I'm going to put DNE, and then I'm going to move on to the next, and then I'm going to go home and play Madden football all night long, right? And then I'll be 35 years old, living in my parents' basement, and they don't even have a basement. I know, so I guess I just have to live in the broom closet. As long as I got my Madden football, I'm good. And when they go on vacation, I guess I'll feed the cats. No, there's nothing wrong with moving back home. That's fine. You just don't want to stay there necessarily, unless that's what you and your parents want, right? Whatever. I don't want to say that's a pejorative thing, because as a parent, I know that I would welcome my kids back at any time if they fell on hard times, but I would also be like leaning on them towards the front door, like, you need to make sure you get back out there, buddy. Right? There's right, go. All right. F of negative 13. So I wrote it down. Now from the home screen, alpha trace, enter of negative 13, right? Negative 13 was not on our graphing screen, and that's why we got an error. So rather than change the window over and over again, let's just do it from the home screen. We hit enter, and we get, I'm going to put side by side here, equals negative 4860. That terminates, so we don't need 3 decimals. Now, is it going up or down there? I like giving you negative values, but it requires you to do a little bit of extra thinking. What would be a value that is now a tenth to the right of negative 13? Negative 12.9, right? Yeah. A lot of people think magnitude, right? So like, oh, 13.1, negative 13.1. But no, that's to the left. So to the right would be negative 12.9. So again, you don't even have to write that down. You just have to get the right answer. So we do have to write this down, f of negative 13. But alpha trace, enter, of, open parentheses, negative 12.9. Boom. And we compare those numbers. So in the future, in the very next instant, my number was negative 4751. Is that number bigger or smaller than negative 4860? It's actually bigger, right? Someone last period said, no, it's smaller. And I'm like, no, it's not smaller. And the person said, well, it's smaller but bigger. And I'm like, no. Say what you mean and mean what you say. It has a smaller magnitude, but it is in fact a bigger number because it's less negative, right? That's what you want to say. You don't say it's smaller and it's bigger. It has a smaller magnitude, but it's bigger because it's less negative. So in the future, if something is bigger, your function is what? Increasing, all right? So we'll say f is increasing at x equals negative 13. There you go. Now, of course, if you know what the graph looks like, and you know that there's no other funny behavior happening outside the screen, negative 13 is going to be off to the left here, which means it's going to be somewhere down here. If you know the trend of the graph, right, you could say, oh, it's just increasing through there, right? And that would work. That would work too, okay? All right. We could skip part C because it's the same thing. But let's jump to part D real quick. Find the y-intercept. How do we find y-intercepts? when x equals 0. So if I throw this question at you, that's me asking, do you know how to find it? So you communicate that by saying f of 0 equals. Now, you could do it right here from the graph screen if you want. Hit 0, enter. We get 2. And again, the cat's out of the bag, right? Look at the blinking cursor. Is the function decreasing or increasing there? It's decreasing, right? So we'll say f is decreasing in a complete sentence at x equals 0. We always refer to the x value. Now, from the home screen, we would do this, right? We would hit alpha trace enter of 0. We get 2. And then alpha trace enter of 0.1. And we would see that it's what? Smaller. Yes? Smaller. Now, because there's like 10 seconds left, I want to show you the calculus part. Okay? The derivative is a function that tells you if the function's increasing or decreasing based on its sign. So you can actually find what's called the derivative at that point. From the home screen, if you hit Math 8, you type in the derivative with respect to x, you recall your function, and then you type in the x value 0. We call that the derivative with respect to x of our function at 0. If this number is positive at this point, the function's increasing. If this number is negative at the point, the function's decreasing. We get negative. It's actually -3. The calculator is trying to tell you that it's -3 because you're the boss of the calculator, right? I think we've had this discussion before, right? If you see at least 3 9s and another 9 or an 8, that's your calculator's way of saying round up magnitude-wise. Or if you see at least 3 zeros with another 0 or a 1, your calculator's telling you to round down. Now, because it's a negative number, f is decreasing at 0. But look, if the number is -3, we not only know that it's decreasing, we know how fast it's decreasing. Like if this was a ball that was falling, we could say the ball at that point is falling negative at 3 feet every second. 3 feet per second. This ends up being the velocity, the instantaneous velocity, which is what Galileo spent his whole life trying to find, and he never was able to find it. We just found it on the calculator right here in the last 10 seconds of class. It was a long 10 seconds, I'll give you that, but yeah. Now you don't have to do it that way, but that is a preview of coming attractions. Some people brought that up, so I thought I'd share. Okay, tomorrow we're going to finish E, F, G, and H, and then we're going to look at a couple of other equations that we have to actually zoom in to find the details and then zoom out to find the details. Finding a reasonable graphing window is a really, really important skill. And it's really not so much trial and error, it's so much educated guessing, refining and tweaking, okay? And then we'll test on Thursday over the calculator. So if you don't mind, go ahead and clear your calculator memory, right? Second plus number 7, click to all, hit enter, verify, and then turn it in with the screen facing forward in the correct slot. Okay, fantastic. Thanks, everybody.